So, yes, so as I think as I announced it to explain both questions, so you have to submit whatever it was, 60%? Did I mention this? Something like this? 50? Yes. Okay, well, let it be 50, okay. 50% of exercises to be admitted to the exam. So that one of the corollaries of this theorem is that Simone has to record some points. Otherwise, how would we know whether you did pass or not? Okay. And the other thing, so last time I was just trying to give an introduction to the problems of enumerative geometry, which is sort of the main purpose of calculations that we are going to be doing. And so first I gave you the idea of this homological version of intersection theory that's necessary, and then I explained the Chow group. There was a small mistake because for some reason, I understood that you already heard of what a Chow group is, and apparently you didn't. So that part turned out to be a little much too quick to compared to what I intended to. So maybe, in any ways, it's not such a bad idea. So the first lecture, I gave you some sort of introductory thing, and in the second, I will maybe start from a little bit from the basics, and I will give you sort of a crash course in algebraic geometry the way I kind of would do it. Of course, you already had a huge crash course during the fall, a different kind of crash course, and this is just going to be a short thing to remind you of things. So I will sort of restart and quickly re-explain this whole thing about Chow groups, but from the beginning. So obviously, I'll not prove a lot of things, but I hope that conceptually these things will be clear. There were some questions, for example, what is reduced, etc. So again, I presume that you know these things, but not a problem. So I'll start from the basics. So now there's no, for now, I will assume eventually that you know what homology and cohomology is, but like zero algebraic geometry for now. So I'll explain whatever I understand of algebraic geometry, which is not so much, but so the idea of so this is crash course on algebraic geometry. I mean, it's really just a review rather than a course. So we start with affine algebraic geometry, and algebraic geometry has a very fundamentally built-in function space correspondence. So the affine case, we look at that means we look at affine k-dimensional space, and the corresponding object is then, so this is the corresponding object is the ring of polynomials. I'll look over complex numbers. This is actually a sure sign that you're not an algebraic geometer if you immediately say that you look at complex numbers, because of course the whole point for them is to look for different fields, but for us this is going to be fine. If towards the end of the course I'll learn what happens over other fields, then I'll tell you, but for now this is okay, going to be okay. So this is this space functions on this space correspondence, and then one extends this by looking at, say, I look at an ideal here, and the corresponding thing then is what we call a scheme. Let's say X sub I, so the scheme corresponding to the ideal. So this here is a tautology. A scheme is just the same thing as an ideal. There's no difference. We call a scheme is just the geometric object which corresponds to an ideal, but it's not something new. It's the same thing. Okay? Now, so the first important thing is that if we're really, this is not really a subset here. If we really want subsets, then we have to go into this story that's reduced. So a reduced scheme this really is a subset. So we can think of this as a subset here. And then we need to take specific ideals, and it's kind of obvious, the condition. So the condition is that we have to, this is a bijection, we have to look at ideals such that, what's called reduced ideals. So we put in the condition that, so an ideal satisfying the following property, that f to the power n is in I, implies f is in I. Okay, so that's the reduced condition. It's kind of obvious, because if I want to think of this correspondence, and here I have all the functions that vanish on this set, then obviously if a power of a function vanishes on a set, then its function also should vanish on a set. So we cannot afford to have a function, a power of a function in, and the function itself not in, if I want to talk about sets. For schemes, this is permissible. And so the basic example that we have is if I just look at A1, k equals 1, and I look at this, then I just have one variable. If I divide it by x squared, so I look at the ideal generated by x squared, then I get a scheme. I get as a subset, it's going to be just the point 0, but it's a two-dimensional ring, right? So it's just it's two-dimensional, 1x, and x squared is already 0. This is a ring corresponding to this variety. Okay, this has an element x such that x is not 0, so it's not in the ideal, but x squared is in the ideal. So it doesn't satisfy this condition. Okay, so this is, if I want subsets, I look at reduced schemes, and then in addition, we're often interested in what's called varieties, and that's the irreducibility. So irreducible. This is a really annoying thing, by the way, about this whole thing, is that one thing is called irreducible and that is called reduced, but these two things have nothing to do with each other, right? So reduced schemes, then we call this a variety, an affine variety. And so, okay, so it corresponds to the ideals that are in addition to being reduced as prime. So we have these two conditions. This one, plus we have the condition that if fg is in I, then what do I want? Fg is in I, then so say f should be in I, or g should be in I. I guess that's what prime is. Okay. So, but that just means that it just has one component. Okay, so this is the basic language. Now, next, so one thing that we use, now we can look at now sequences of varieties that arise. So we can look at a variety and inside another variety, for example. So in any case, we have the Zariski topology. I'm sure you've seen this topology. And this is just the idea is that the closed sets are the subvarieties. Indeed, to check that this works, right, you just need to check that it satisfies the basic axiom of closed sets, that the intersection of two closed sets should be a closed set, right? So we need to intersect two varieties, or two, maybe it's better to talk about reduced things. And so the intersection should be just correspond to the sum of the two ideals, Ix plus Iy. Okay, so this is how we intersect things. And of course, here is why you will immediately see what the problem with this whole story. Why do we need schemes even? Because it's perfectly possible that you intersect two varieties and you get a scheme, right? So the simplest example. Actually, yes, so why did I do this in fact? It doesn't matter. Okay, so the simplest example, for example, if you are trying to intersect y equals x squared with y equals 0, then you can easily see then you take the sum of these two ideals, and this is just equal to, so this, by this I mean now not the set, it's the corresponding ideal now. So maybe let's note it this way. Sorry. So the ideal generated by x squared, and the ideal is generated by just y equals 0. If you intersect, obviously the same thing as y equals 0 and x squared equals 0. And, sorry, why did I say intersection? Now it's sum. Sorry. Okay. And so this clearly has an element x whose square is in it, but x itself is not in it. And so, so this is not reduced. So you can have two reduced things, so just a parabola and a line, and the intersection is not reduced. So it's possible, so actually it's better to write here actually subschemes maybe, because then we don't have this problem. Okay, and so Zariski topology just says that we look at the closed sets, and this also allows you to define the dimension of X. It could be defined, for example, as a chain of subvarieties, right? The length of the chain of the subvarieties as the length. So you start with X, and you look at X1, etc., all the way to X0, which are just points, and so then X, the dimension.
The maximal length of the chain?
Yeah, maximal length. Okay. So that's all, so you get a topology and you get a notion of a dimension. And as I said, so one of the reasons motivating this idea of introducing scheme instead of just varieties, so instead of subsets, we look at these more complicated things, because intersection actually only makes sense in the world of schemes. Okay. Now, so maybe, yeah. So another point is that, okay, so this was the affine story, then people talk about general schemes. When they glue these schemes, so I'm sure you've seen this, right? You had schemes in previous semester. No? Yeah? No? Anyway, you had some schemes, but we are not going to do this complicated thing because it's complicated. So we are going to do a slightly simpler thing. So first of all, you can look at now from affine, you can go to projective. Schemes, I'll call it. But what I mean is that, and in general, projective stories. So that means that the whole thing you can again try to say in projective things, except the only thing is that you will have to look at everything. You look at homogeneous ideals. So what I mean is that they are generated by homogeneous polynomials in the variables x0, xk now. Okay, so you look at this ring, but now you look at homogeneous ideals instead of arbitrary ideals. Obviously, in this case, then in projective space, you'll have subvarieties, subschemes, etc., etc. And in fact, clearly, if you setting in PK, setting x0 to be 1, this is just going to reproduce for you the affine situation. But this way, you can have set other variables to 1, and then, so this is a homogeneous coordinates, right? So pk. I'm not going to explain what pk is because otherwise, right, I use this notation. If you set one of them to be 1, so it cannot be 0, then you just get the affine space, and you get these affine charts. But so you can do the same thing in projective space, and then a slightly more general situation is something that's called quasi-projective. And so then it's simply that you take a projective one like this, so you define the same, so everything is identical. Ideals, reduced, all these things remain the same. But Quasi-projective varieties, you allow one thing, you're allowed to throw away one. So it's an open subset, if you like, open in a projective variety or scheme. Sorry, sometimes I say variety when I should say scheme. So one in open, so what I mean by that, so you see I defined topology. This is always this topology. So closed is something that's a subscheme, so it's the complement to that subscheme that you take. That, if you like, it's given by a pair of a projective scheme and another projective subscheme that you throw away. Okay. And this quasi-projective is going to be enough for us. So this is the most general schemes we will be looking at, just quasi-projective schemes. Okay. So if you have the feeling that I'm cheating a little bit, then you're right, but it's not important because anyway, I think algebraic geometry is not a subject that you should, well, that's what I think. You should learn from the very beginning and really learn everything correctly, because I think just very few people get to the end that way. I mean, they are people, and they become algebraic geometers, but if you want to really become like, so understand, say, enumerative geometry in a semester, then it's much better just to jump through certain things. I mean, I think you have a pretty good picture now what's what, and then, you can go back and ask, but what the heck is that really now? What are the function fields, etc. on that? And so there's things you can do, but I think you should have at least a basic idea of competence. So now the next thing we need is smoothness, smooth points, right? So, well, let's now assume that X is a variety. And so we can assume that it's defined, maybe actually, sorry, let me just start. Apologize. Let's say it's a hypersurface. Hypersurface. So hypersurface means that its codimension is 1. Means codimension is 1, and in fact it's easy to see from basic algebra that in this case the ideal will be generated by just one element. So the ideal is generated by one element. So the ideal is just going to be generated by some function f. Okay, and this is, you can use both situations. Now in the projectives case, you have to eliminate one of the coordinates, but so in the affine case, you just look at a point, P in this X, and you say that, now it's a definition, so P is smooth if you take the gradient of f, df, so you take the makes of partial derivatives. I'll denote this by df, so that's the gradient at p is not 0. So you take the partial derivatives, and if at least one of them is not 0, then it's a smooth point. Otherwise, it's not. Okay, so that's the thing. So this is very well defined there. As I said, in the projective case, you look at one of these charts. So if x0 is not 0 in P, you just set x0 to be 1, and then when you're an affine chart, it's a local property, and you check the same condition there. Okay? In the quasi-projective case, it's the same thing, because obviously once you are on a point, you basically are in projective space, and then you do the same story. Okay? So this is smooth. Now, for a hypersurface, if you want a more general, it's basically the same thing. So as I said, there's a notion of codimension, and if X is just, say, a subvariety, then, or a variety, Then you do the same thing. Well, now at the point you are, say, generating the ideal of x is generated by some functions f1 up to fp, fm, and now you just look at the Jacobian matrix of the f, so this, and you look at the point p, and you look at its rank, and it's again the same thing. What you want is that this should be the codimension of x. So this condition means that x is smooth at p. So this is a little, so I'm mixing two things here a little bit. So of course, in fact, if this is the case, if the point is smooth, then the number of functions that defines the ideal, at least locally, will be the same as the codimension. You can cut out by as many functions. So what I'm trying to say, in this case, at least locally, around the point, one can take so locally near a point, you can take as many functions to define locally the ideal as the codimension if the thing is smooth. But a priori, this is not true. So a priori, you just have to take all functions. So that's why this m is there, which is not necessarily the same as this codimension of x. I don't know, is this clear what I'm saying now? So normally what happens, actually, it's a little confusing at the beginning when you think about this, is that suppose you have a subvariety and you start constructing these generating functions. So you take one function, that cuts down the dimension by 1. Then you take another function, cuts down the dimension by 1. And you just continue doing that. And usually what happens is that you create a bunch of components outside. So these functions vanish. So this is your variety. And then you just take sort of one function and then another function. And so they will have some common zeros in an outside components away from when you just add these functions. So you have to introduce new functions which are not zero here so that you should eliminate that. And that's sort of what is really happening. OK. All right, so we define what smooth, and so what smooth point is. And so then we can also define the tangent bundle. So I'll just actually, there's a tangent cone more generally, but if P is smooth, a smooth point, then I can define the tangent bundle. X is just, well, it's a linear space, and it's basically just if you like, it's the image of the, what am I trying to say? It's the, so this is the codimension, so I just look at the tangent bundle, say, of the affine space where it's embedded, and then you get rid of the image of this Jacobian matrix, right? So okay, so well, it's sort of the obvious thing. I mean, in this case, it's the easiest to understand. Like you have in the hypersurface case, you just have here's, you kind of your sphere. Your function f is sum of x squared, right? And sum of x I squared equals 1 is the sphere. And then you just look at the gradient of the function. That's this df. And then you just quotient the three-dimensional space by the gradient vector, and then you get the tangent two-dimensional tangent plane for the sphere. And it's the same thing is true in general. So you just take, well, this is just AK, of course, and then you just quotient by these vectors that you get as derivatives, gradients of the defining functions. Okay, and so finally I defined what transversal intersection is. If you take two varieties and you take a point in the intersection, then we say that, and suppose you are in an even larger variety, V, then the intersection is transverse. So the intersection is transverse if TPx plus TPy is equal to TPV. So X and V are, of course, sorry, so that's not quite correct. What I meant is that both X and Y are in V here. Okay, so that was a definition for transversality that I used last time to define intersections. Okay, finally, maybe one last thing that I did not mention last time, and this is which I'm sure you've seen. And this is Bertolini's theorem. So we'll look at the projective case. So let's consider, so first a notation. So if I have this pk thing, then I can look at the dual, so basically the projectivization of the dual space, right? So what I can define this pk star space, which is simply the projectivization of the dual, and each point here then, this is just the hyperplanes in pk. Right, so the space of hyperplanes in pk forms another projective space, which is just sort of the dual projective space. And Bertolini says the following, I'll maybe say slightly more generally, is that no, pk.
What is a hyperplane?
So yes, so we call it a hyperplane. It's everything is projectivized. So for example, X, so this will be important. So you have pk. So this is given by these coordinates, right? So you understand this notation, this double dot notation, right? Okay, so the point is that now usual equations do not make sense, since this is really an equivalence relation here, that this thing is the same as if I multiply everything by 2, right? So they don't make sense, but homogeneous ones do make sense. So let's write down a homogeneous equation. So the general one I care about here is just say the equation's a linear one, sum of gamma I xi from 0 to k. These are just numbers, the gamma i's. So this is an equation, and this equation gives you a subset of P because the equation is homogeneous. So because it's homogeneous, it's meaningful on P, pk. And the zero set is a hyperplane. Of course, it's hyperplane, it's a little strange, but I mean, just call it a plane because it's not a plane, it's a projective plane. Okay, it's clear? So that's what I call hyperplane. And now the coefficients, these gammas, now, if you like, this one, this point now, the point is that now it's dually also true that this hyperplane is only depends on gammas up to a constant. So now I can take the point gamma 0, gamma 1, gamma k. And this point now is of course not in pk, right? Because the pk is given by the coordinates x. It's in some other space. And this other space I call pk star. The space of gamma, k plus 1 tuples of gammas. Okay? So you see, if I take a k equivalent of gamma here, then I get an actual subset, which is now a hyperplane here. So a point here gives you a hyperplane here. That's the correspondence. All right. So what did I want to say? Yes, Bertolini. So Bertolini's theorem says the following pretty fantastic thing. So here, let's start with x, some nice variety, say. So then, according to this thing, in fact, we'll have x can be written as x, so smooth, so the smooth part, and X singular. So I just take the set of smooth points according to that definition, and the rest is the set of singular points, non-smooth points. Okay? Yeah, I will maybe confuse this thing. What is singular, regular, and whatever. So there's some difference at some points, but anyway, just between smooth and regular. But as I said, I'm not an algebraic geometer, so these definitions are correct nevertheless. Okay? So now one important point is that the singular, this is actually is an algebraic condition, and this is actually a subvariety, in fact. Of X, the singular points, that's closed. So it's given by some equations, in fact. And this will be according to the Zariski topology, so that means it's going to be some open subset. But it's just that I just mentioned this. So I'll not write lower than that, so I'll erase this stuff. And so now what I will do is I just take a generic, so the statement, so the Bertolini theorem now, Bertolini says that if I take for a generic, and now generic, I use this thing, that just means it's a Zariski open. Open, right? So here, for example, a generic point of X is smooth, right? Because it's a Zariski open. So to say generic just means that the complement is contained at least in a subvariety. The complement is a subvariety. So it's given by equation, so it says lower dimension. So for a generic gamma in pk star, so did I assume, no, sorry. In a variety in pk, say here. In pk star now, so in other words, for a generic hyperplane, if I take the intersection of X and this hyperplane gamma equals 0 is transversal. So according to that thing, and as a result, actually, and thus, sorry. No, I made a mistake. I wanted to say two theorems, and now I confuse them. Just a second. It says, say, away from X sing. Of course, I didn't define even what. So I only define what tangent space and transversal is for smooth points. So if it intersects X sing, then it's and thus, so as a corollary, if X is, for example, smooth, then for generic gamma, X intersection gamma equals 0 is also smooth. Okay, but actually, is this clear? So if you have transverse intersections, then this gives you smooth things. But this, the way I formulate it gives you a little more, because imagine, for example, that you have just one point which is singular, right? So, but this is more, gives actually more. For example, suppose that X singular is just a point equals Q, just a single point. Singular, everything else is smooth. Then, according to this, I can just look at all the hyperplanes where, I just look at all the hyperplanes which do not intersect this, which do not contain this Q, and that's a closed subset of the hyperplanes. And then then away from that, I can still, if I take such hyperplanes and look at the hyperplanes whose intersection with X is transversal, and I still get smooth things. So in other words, if you take a singular variety whose dimension is at least 2, and it just has one singular point, then a generic hyperplane sections will still be smooth. Hyperplane section is still smooth. Okay, so that's what we get out of this. And we can also we can iterate now this story. So we can take several hyperplanes, right? Because I intersect with one, and then I take now this subvariety. I start intersecting with more hyperplanes, and this can be iterated. So I can take, say, gamma 1, gamma 2, two generic hyperplanes equals 0 intersecting X is generically smooth. Generically. If, for example, X is smooth. Okay, so this is Bertolini's theorem. Okay, I'll not prove this, it's not difficult. Okay, so now we go to, so this is the basics of algebraic geometry that you need to know. And so now we define these Chow groups. So you remember the idea was that we looked at the cycle. So X is actually any scheme. There's any C missing, scheme. And then we define ZX, which were just the formal sum of subvarieties and then we define the rational equivalences, which was constructed as maybe I'll use this notation: f say 0 1 minus f 1 0 is generated by this, which is generated by this linearly, where phi is just a subvariety in so here's X and here is P1, and phi is a subvariety not containing any fibers. I explained this last time. So just a subvariety. And now we'll look at phi 0 1, the intersection phi 1 0. And so these now we define using the intersection theory that explains. So the great thing is that I explained at the beginning that intersecting schemes, well, so there's some subtlety that you might get even intersecting varieties. You can get schemes, but it's very easy. Just take the sum of the ideals, okay? And so this one, say, phi 0 1, you can just think of this. It's in here. This is phi 0 1. By 0 1, I mean, well, maybe I should just double dot, sorry. So what I mean is just its points on P1. It's the fiber here and the fiber here, and I just think of intersecting phi with this fiber, right, with P1 that's there. You get a sub-scheme this way here.
Or should we switch what P1 and X are?
Pardon?
Shouldn't we switch what P1 and X are? Because phi should intersect.
Yes, we should. Thank you. This is not very good. Okay, well, thank you. All right, so this was And then we define the quotients. So now I need to stop, right? Yeah, I'll stop now. Okay, and I'll continue. So I'm sort of before where I was last time at the beginning, but anyway, this does happen. Okay. So we had this definition for the Chow group, so I just want to point out that one can alternatively, if you remember, so the divisor groups, you had defined divisors on varieties last semester, then you can have an iterative procedure to reproduce that notion starting from divisors, because, well, essentially, if you have now it's just going to work in codimension 1, but let's X be now a nice variety. So then if you take a function f, or roughly, this is not completely precise, but a rational function, then you can think of it as a map from f x to p1, and then you can look at the graph, the graph gamma in x cross p1, or x cross p1, gamma f. Right, so you can think of rational functions as functions from x to p1, and then you can look at their graphs, and they will produce. This is not completely correct, I think, but essentially it's correct. I mean, just as you'll see, I'll make a statement. In any case, the point is that if you take rational functions, then this gives you an element in the divisor group div f. You know, the poles minus, so this is poles minus zeros, and the equivalence of now, if you just look at the similar thing, formal sums of divisors, so this sum and you quotient instead of the rational equivalence, you just quotient by all of these. So this, you had a name for this. This was the, I don't remember, Picard group or something. So this is the same thing as that thing, okay? This is just equal to, so this is a statement now, that this is equal to what I defined there. Sorry, I didn't finish it here, sorry. But you remember this. I mean, I did this last time. So x is equal to z x by this rational equivalence, and this is graded by the dimension of the subvariety. Okay, so I explained this last time. So all I want to say that this Picard group is actually just going to be the same thing as the Chow group in codimension 1. So this equivalence of divisors is the same thing as its rational equivalence. That's all. So what you saw there before, you saw examples of these Picard groups is the same thing as that. Okay. So you have this shows you that there is certain complexity. This is not so easy, right? Because this Picard group is not such a simple thing. It could be it's certain, it could be infinite dimensional. There's lots of problems. So it's not so easy. Okay. And then you can actually iterate this procedure to define using divisors in subvarieties to define this thing. But I'm not going to do that now. Okay. So one point is A is complicated. I mean, this could be a very difficult thing. Right? For curves already, it could be very difficult. Okay, and so then last time I introduced a bunch of objects which were important, so I just quickly remind you of the thing. These are relatively easy part. So one was that I simply take the same thing but graded by the codimension, and I'll call this is the same object. So A, so I define A upper C of X as by definition is just the Chow cohomology, if you like. Definition is just A of dim X minus C. So it's just graded by codimension. And then there are maps from there are maps from dim from A say D of X into the homology of X. So I explained last time that the homology of X is a relatively simple, at least it's finite dimensional, some kind of calculable thing. This thing could be incredibly complicated, but certainly for every cycle there is a fundamental class that you can put here. So this thing is well defined. So these are now I'm just defining some objects that we have. Okay, and what else do I need? Okay, so so now, as I mentioned last time, if you have X is smooth, projective, so it's a smooth compact manifold at the same time, then we have the Poincaré duality, which associates to each element what do I want to say actually? Yeah, so it associates, it maps from H dx to H dim X minus dx to the cohomology, which just, it's the Poincaré dual of that subvariety. Sorry, I already made a mistake here. Of course, it's because it's over complex numbers, it's twice here. Okay, and now came this thing about intersection theory and the moving lemma. So theory, moving lemma, so it's if X smooth, actually it's defined if it's just quasi-projective, but we'll be mostly interested in the projective case. Then if you take alpha in AA of X and beta in AB of X, then there exists VW subvarieties or subcycles more precisely, and this you did now in your homework. So such that the class of V is alpha, class of W is beta, and then VW are transversal, generically transversal. Transversal, right? And generically again means that in the Zariski open set, it's of V and W, it's true with intersection, and V intersection W then is, as intersection variety as I explained, is well defined as a scheme. In any case, this is well defined by meaning that if I choose different representatives of alpha and beta, I always get the same thing in the Chow group, in Z, in A of A plus B of X. Okay, and that gives us an notion of intersection in the Chow group. So as I explained, you can intersect schemes the way I explained there. Now, this thing actually descends, it's consistent with rational equivalence. That's what I'm saying, basically. Okay, so this was the moving lemma, and this endows the upper, because it's additive with the codimension, the upper Chow groups with a structure of a commutative associative ring. And it's consistent with this Poincare duality thing. So there is a ring homomorphism, and there is a ring homomorphism from A to, so this is doubling because ring homomorphism, which is neither ejective nor surjective. So in general, it's, but anyway, so this is kind of a algebraic imprint of cohomology. Okay. And so finally, the last thing that's important then there is the so I'm just repeating what I did last time, but just now that you didn't done your homework, maybe it's a little easier. If you did. If you didn't, then it's not so much easier. There, one can define, so X, Y is a morphism. So one can define this gives rise to F lower star, which maps A. So when I put this dot, so if I write this, then what I mean is that the degrees here are the same. So it's a graded morphism. So I will be consistent with that. If it is a change, if it's a higher one, I put +1 here if it changes, but this is correct. And morphism, well, let's, for now, well, this is here. I think it's better if they're smooth. And then there is also a pullback, which now is the codimension that's preserved. And this is consistent with the maps into cohomology, where, of course, all these maps are easily definable. Okay? And these really just correspond to set theoretical things. So you do some technical mumbo jumbo, but essentially it just means that if you had a cycle here in the Chow group, then F lower, so you just take a cycle of some subvariety S, then this is just going to be the Fs. Okay, well, here there is some correction term with the degree. I explained this last time. But essentially, it's a set theoretical push forward. So you take the image of the set, and then you, with some correction. And here, it's similarly F upper of some subvariety V of Y now is just equal to just the class of, sorry, I did something wrong here. Sorry, this is wrong. No, what I meant to say is this, that you take the class of the image. And here, you take the class of the inverse image of V. Okay, so I put these inverted commas there because there is some technical, you have to put them in transverse position, or something I explained this last time, but essentially that's what we're talking about. If you, and so this called permanence equation Sorry. So now I will be more precise, as I didn't have time to explain last time precisely, is that this thing is a ring homomorphism. So I want to explain this a little better now than last time. It's a ring homomorphism. It's easy to see. And so just like in the case of cohomology. And so since this is a ring homomorphism, so that means that, that AX AX is, I think it's right, just a second, is an AY module. Or yeah. Okay, so when I say ring homomorphism, right, so I can define a module structure of AX by this image here. Right, so what I mean is that AX is a ring, this is a ring, and you can think of a ring homomorphism as just saying that that F star A B multiplied by some C is equal to just F for example. I think it's this, something like this. Yeah. Okay. So that's yeah. So this at the same time says that this is a ring homomorphism, that this is the same as this, and also that it gives an AY module structure. So then the permanence equation says that this F lower star is a that F lower star is an AY module morphism. So what it means is that if you take F lower star of, so you take some alpha here and multiply it by F upper star beta. So you take an alpha here and a beta here. Then this will be the same thing as if you just took alpha and multiplied by, the push forward of alpha and multiply by beta. Okay. Okay, so this looks complicated, some algebraic mumbo jumbo, but maybe this will going to be exercise to check that this is some completely elementary thing. So that this is just means that you have, that you can, either you can first push forward and then multiply, or you can just multiply first by this thing which is which is according to this is just the same. We think of this as the same element, beta and F star beta. First multiply and then push forward. So these two things commute modulo that we identify beta and F star beta. And this identification goes through this thing here. Okay. All right, so this is some very simple thing in the sense that this actually, that's why I wrote this down, the proof is just you check that these things are true set theoretically. So what I mean is that if you just check that, that F of, with some degree correction of F of A intersection F minus F inverse B is just the same thing as F of A intersecting B. So that's what this says, and it's true. Okay? So we'll need this, you'll see in a second. Okay. So we have, in other words, in short, what you have to keep in mind that we have this strange thing. We have these lower and upper graded equivalent sets, the upper and lower Chabgroups, which are really the same with a different grading. The upper ones form a commutative ring for intersection, and the lower ones are not. They preserve the dimension, but they do have this property, this strange extra property, so this extra structure. Okay, so this is what's a little bit confusing. Okay. Okay, I think I'm done the preparation, so now we go on. I still have 20 minutes. Okay, so we'll do everything in 20 minutes. Okay, so the so the idea is why we did this whole thing, because we'll do now calculations. And of course, as I said, calculations are unbelievably complicated in general, because this thing is much more difficult than homology and cohomology. But there's a case when it's actually much simpler, in a sense. I mean, it's easier. This case is still pretty general. You can get a lot of mileage out of this. So this is what we're going to do now. Okay? So the notion is, anyway, this is very useful, is stratification. So suppose X is some, well, let's assume it doesn't actually have to be smooth. Just some variety. And so stratification is the following thing, that you take X is just going to be, this is, by this I mean disjoint, yeah? This means disjoint, you mean, this star. Of sorry, UIs of sets which are, well, quasi-projective subvarieties, or just union of subsets if you like. And what is true is that the condition is that if you take the closure of UI, so actually I'll introduce the notation already. So let's YI be just the closure of UI. And these are actual subvarieties. Okay, because closure in Zariski topology, of course, is a subvariety. The closure is closed, and closed means it's a subvariety. And so the stratification condition, so this, of course, you can do many ways. You just chop it up into different pieces, is the following, is that, maybe I'll do it in this fashion, that I is just equal to, so UI, if you like, plus the union of for all the Yj such that J is in Yi but is not equal to it. Or maybe, so this is the stratification condition. Or maybe another condition is that if I take, so this is equivalent, that if I take UI and I close it, then this will be a union of some Uj for some subset. Here's some for some J, index set J. So I take J and J. Okay, so I'll explain in a second what this means. So what we allow and what we don't allow. Okay, so this looks complicated actually. This is actually not a very intuitive definition, but it's easy to understand. I mean, let's maybe just look here. So the idea is the following. You have some set, Yi, so this is the same thing. And so it has some open open part. So this is, say, ui, and this whole thing is yi, for example. Now, what I don't want is the following. So here is the boundary, and the boundary has to be unions of uj's. So what we don't, and the uj's are disjoint. So what I don't want is something like this. So I don't want that there is a uj which actually goes past this, because since this point is in the closure of ui, so in this union I will have to take uj in, right? Because this is the only, uj is the only element that contains this. They are disjoint. So this, I have to take uj when I form this union to represent the closure of ui. As a union of other uj's, I take ui, and then I take some things in the closure. But if this point is in the closure and it's in uj, I have to take uj in. But once I do this and there is this part, this interval is also in uj, then I will have to take points in which are not in the closure. And that's bad. So this is not a stratification. So this is not a stratification. So you can represent sets as disjoint union of things, but this is not allowed, this tail here. Okay? Okay. So that's the condition, so that we disallow the tails, basically. Okay, it's called the stratification, and then definition. So this is a definition, really. And then there is, in addition, additional definition. So we call the stratification is affine if ui, for each I, there exists some k such that ui is just the affine space. So it's just if the pieces are some affine spaces, that call it affine. Okay, that's not so surprising. And we call it quasi-affine. So this is affine. This is stratification. So that's, I define, this is a definition of stratification, is basically this condition here. The affine condition is this, and it is also, we call it quasi-affine. Sorry, quasi. Stratification. And then we just want ui is some open in set in some ak. Right, so we throw away some closed set, but it's not the whole thing. All right. So then the theorem. If x equals ui is a quasi-affine stratification, then the Chow group of x is equal to the sum of the Chow groups of, so it's the sum of the Chow groups of, sorry, maybe, just a second, sum of z times yi. So what it means is that then these things that in the quasi-affine case, these well, the closures, because we have to, the closures are some subvarieties, they actually generate the whole thing. And so it's, for example, it's not going to be infinite dimensional, it's just going to be some relatively simple thing. Of course, they might, but the reason I write a sum here, there might be relations. Right, so clearly, for example, if you take P1, you can just represent it as C star plus North Pole plus South Pole. So as a disjoint unit of three things, it's a stratification. But north pole and in the Chow group, the north pole and the south pole is the same element of the Chow group, as if you did your homework, then you know that. So there's a relation, but they do generate. So is this clear, what I'm saying here? This is now important calculation device. And sorry, so I'll erase this because the second part, if affine, so instead of quasi-affine, now I have affine, then amazingly, what is true is that AX is just equal to the direct sum of ZYI. So what it means is that these are linearly independent. Okay, so that's really fantastic. So in particular, so let's use this. This is, this is incredible, by the way, that this thing here is, actually, I forgot to mention, this is Totaro's theorem, and this is 2014. Okay. But in fact, sometimes it happens. People prove theorems that make life so much easier. I mean, before this you would need to study 2 years before I could explain what I'm explaining now. Now it's much easier. So, okay, since we have this, so let's identify now. This immediately allows us to identify, for example, the Chow group of Pn. So the Chow groups of Pn or Pk. What happened with this? Okay. So what do we do? Well, it's easy. I mean, now we have this P0, which is just a point, P1, Pk minus 1, Pk. And we think of, so this Yi will be just Pi, right? So the subvarieties that I'm talking about. And the Ui's are, of course, just Pi minus Pi minus 1, which is just a I. Right? It's precisely those affine spaces. Okay, so here I just take, so you understand this? I don't need to explain this, how this goes. I mean, you just take the coordinates and set some of them to 0 and this. Okay, so, and it's easy to see that this closure condition is satisfied. I mean, it's basically obvious because we only have one for each, so you can't be any other way. You can check that this is affine. This is an affine stratification. And so the Chow groups of Pn, Pk is just direct sum of Z Pi. So in each dimension, it's one-dimensional. Okay. And moreover, but this is a ring now, so we also define the ring structure, but that's really easy because we know, of course, how hyperplanes intersect. That's sort of what you were also doing in your homework, intersected hyperplanes. So let's call Pk minus 1, the actual hyperplane, the class of this, by just call it, say, alpha. Okay. So obviously, alpha square is equal to, so you just take two hyperplanes, H1, H2. So these are two hyperplanes. When you intersect them, I mean, unless they coincide, they're already in general position, and it's just going to be, obviously, the codimension 2 linear subspace, which is precisely Pk minus 2. Okay. So I mean, you just by hand can't. You remember we just set theoretically intersect two hyperplanes. You get precisely a projective, a codimension 2 linear subspace. And so I can actually, instead of this, I can say that this is alpha and then it's alpha squared and etc. You can continue this to actually prove that alpha to the j is just equal to p k minus j. Okay, just the same way. It's just simply linear spaces and linear intersections. And so this means that we have the identification as a ring. We have that A of pk is just equal to, so it's a free generated by alpha, a free polynomial ring generated by alpha divided by alpha to the k plus 1. Okay, because of course. Okay. So now I will introduce one more piece of notation. And this is, what we can do now let x be, let's say, subvariety, So then of dimension d, say, well then, it will always be a pure subscheme, but I let it be a subvariety. Then you remember x, by definition, is a class in the child group of the correct dimension. And it's only one. But the thing is going to be in z of alpha to the power k minus d, right? Because, again, in each dimension, what we see, in each dimension, this child group is one-dimensional. So it has to be z times that generator. And it's the codimension when you take products that appears here. This is sort of the Poincare dual. So in other words, there's a number here. So x is equal to some degree x times alpha to the k minus d. And that's the degree, the definition, if you like. It's the definition of the degree. It's that constant. Okay? All right. So I just very quickly want to show you a calculation. I hope I still have time for that. Next thing is very easy. Same argument is what happens if you take the product of two. So by the way, it's a bit annoying, but if you take the product of two varieties, then the Kenneth formula tells you that the cohomology is also the tensor product. That's not true for child groups. So it could be more complicated. But in this affine thing, our theorem actually implies that it's true, because once you had product of two stratifications, again, going to be a stratification because the product of affine spaces is affine. So this is still true. So you get the completely analogous statement as just z alpha beta divided by alpha to the r plus 1 and beta to the s plus 1. So it's exactly the same thing, because you have the same stratification business and the same arguments about intersections. So it's the same thing. Okay? All right. So what I wanted to explain is the following. So this is, so let me just explain this last thought here. Suppose that I want to identify, I take, say, this, it's called Severi or Segre, now I forget now. One of the two. Anyway, I'll remember next time. But I take this standard map from PR, PS to P, so I'll take a little more time maybe. R plus 1, S plus 1. I mean, I'm sure you've seen this one, this map. And so what I do is that I have x0 up to xr, y0 up to yr. And then here I just go to xi times yj. Right? So I just take all pairwise products of variables, and I just construct this quadratic formula. Okay, and so this you have this many coordinates plus 1, so you have r plus 1 coordinates here, s plus 1 coordinates here, so you have r plus 1 plus s plus 1 coordinates here, and then when you projectivize, you get a minus 1. Okay, so it's clear, the map? So the question is now, the question, the degree of the image. Okay, the image is a subvariety. So by the way, it's easy to see, note, this is an embedding. I'm not going to explain this now. I just want to explain the calculation quickly. Okay. So how do I, so now we know this is a variety, so there is, it's represented this way. I want this number. How do I calculate this number? Okay. And this number, you will use this permanence equation that I had there. So this abstract nonsense here actually is kind of helpful. Okay. Because so what we do is that we are trying to understand what this f star alpha is. So we are trying to calculate the degree, so that this degree is really equal to just this, let's call this now g. So I'm sorry, I'll just take 3 extra minutes. So I'll just take g lower star of this PR plus PS. Okay, and so the degree, well, one way of thinking about it is that they're just intersected here with the correct codimensional thing, which will be just multiplying. So let's call now this something else now. So let's call it zeta, for example, zeta to this power. Right, so here's alpha, beta, and in the image it's zeta. So I'll multiply this by zeta. I don't know how to write it. Zeta, I don't know why I chose this, to the power r plus s, which is the dimension of this thing. If I do this, then I actually obtain an this is now in degree 0, so this is in a 0 of p r plus 1, etc. If you calculate the dimensions, and I just want, oh sorry, I'll lower 0. And I just a set of points, and I just want the number of those points. That's the degree. Okay, so I want this. That's the same thing as this degree. And this degree, now I use that theorem, you see, because I have precisely something like this, f push forward alpha times beta. Okay, so here alpha is just this PR cross PS. So that's terrible, this notation. Now because I denoted that by, oof. So anyway, yeah, I made a mistake. The alpha bar, whatever the thing is just this PR cross PS. So alpha bar that's coming from there. And the beta is just this zeta to the power r plus s. Okay? And we use that formula. So I just want to show you this. So that formula tells you that the degree is just equal to the same thing in the back. So that's just equal to the product of, so basically PR cross PS and then you sort of intersect it with the pullback of beta, of beta, which is zeta to the r plus s. And this pullback, now the point is that pullback is a group, this is where the trick is, that this is, of course, equal, since, remember, f star, that the pullback is a ring homomorphism, that the same thing as just the pullback of psi to the power r plus s. So basically, I just need to calculate the degree of this object, the pullback of zeta in this ring, in the Chow group of PR plus PS. So this is where we win, is that we use the fact that now, using that theorem, this is a group homomorphism, and so it's just a linear object. So let's evaluate the pullback. Zeta, so I don't want to take more of your time. So zeta, it's easy to see, since it's a bilinear function, you'll do this exercise, this is just going to be alpha plus beta. That's easy to see. And so finally what happens, I take alpha plus beta, I raise it to the r plus s, the pullback. I raise it to the r plus s's power, so alpha plus beta to the r plus s's power. This is precisely the pullback of zeta r plus s. And now I just need to calculate its degree, and it's easy to see that the degree is precisely the coefficient to the coefficient of this top coefficient. So it's to alpha of alpha to the r, beta to the s.
I'm sorry, how did you define zeta?
What is zeta? Zeta is just because we have three projective spaces, PR, PS, and PR plus 1, S plus 1, and it's just a generator there. So those are the three letters. But yeah. And now, so the degree here is just going to be the coefficient, of alpha r multiplied by beta s. So really what it is just the coefficient of alpha to the r times beta to the s in alpha plus beta to the r plus s. And this is equal to r plus s choose r, the binomial coefficient. Okay, so that's the final answer. Okay, so this end was a little quick, but I think you know enough so that if I give you some exercise, you'll be able to recover. I mean, this is not difficult from here. Okay.